Perfect. Thank you very much. So in criminology, graphology may be used to link a suspect to crime scene evidence. For example, handwriting sample can be taken from the suspect. Then crime scene analyst can compare the prints to evidence such as notes, signatures, messages left at the crime scene. And similarly, in computer science, the same concept can be applied to programming languages. And we can study the structure of a program to analyze artifacts that can be relevant to discover more. In this presentation, I will talk about code graphology and how to study an exploit code and build a hunting error rule with the information extracted. My name is Thomas Roccia. I'm a senior security researcher at Microsoft, and I've been relocated from France to Australia last January. If you want to see some of my work, you can visit my website at securitybreak.io, and you can also follow me on Twitter and Mastodon. All right, so in this presentation, what will be covered? First of all, I will define what is code graphology and what the concept is exactly. Then I will focus my presentation on a use case, which is a local privilege escalation CVE 2021-1732. And then we will see how to analyze this specific CVE to extract relevant information that can be used to create a hunting error rule. But first of all, what is exactly code graphology? Code graphology is actually a concept that was first discussed in 2020 by checkpoint researchers at Virus Bulletin. And they explain actually how to study the structures of an exploit to extract the information that can be used to uncover additional information. And this concept is very interesting, and it can be applied to malware analysis. For example, if you want to look for similar code similarity for a same malware family, for example, or to identify code related to the same attacker. But it's very useful in exploit hunting, because when you are coding an exploit writers tend to use similar mechanisms that will be reused for multiple exploits. So this is very interesting, and the concept is very well detailed in a white paper they wrote. And you can find more information about it if you're interested about this concept. The CVE 2021-1732 is a local privilege escalation on Windows 10. A local privilege escalation is very interesting for attackers because they allow them to elevate their privileges and run code with high privileges on the targeted machine. This is a highly regarded kind of exploit because it allows to run any kind of code into the targeted machine. This exploit has been first reported by DBAP Security in February 2021, and they reported this exploit and said that the exploit were actually used in the wild a year before the reporting. And it has been used by the Bitter APT, which is a known nation-state attacker that used this specific exploit in several campaigns and several cyber attacks. This exploit is located in the win32k.sys driver, and especially this is a window object type confusion that leads to an out-of-bound write. An out-of-bound write allows an attacker to execute and run arbitrary code into the machine. So let's take a look more to the CVE itself. This is a simplified overview, and I'm gonna explain you all the steps, which are very important to understand from the next part. So basically, the exploit is located into the win32k.sys that we can see on the top. This is a driver responsible for graphical interface. Mainly, a program will use that specific driver to create a menu, create a window as well, and any kind of user interface, graphical interface. Our exploit is actually creating a malicious window with the API create window X and some corrupted byte in the object tag WND CB extra byte. This specific corrupted byte into this object are very important because they trigger the vulnerability for the next part. As soon as the create window, in the exploit, there is also some elements such as the HM validate handle, which is a call to an unexported function from user32.dll. This is what we call a primitives. This is basically a known technique used by kernel exploit to leak a memory address from the kernel. Leaking a memory address from the kernel is very important to be successful in that kind of exploit, to be able to run code from the kernel memory space with high privilege, meaning with high privileges. Then we have our corrupted object, tag WND, that will be used to trigger the next part of the attack. We have client alloc window class extra byte, which is actually a function that will read the corrupted byte and trigger the exploit. Then we have a call to the anti-user console control, which is a function used here to convert the malicious window into a console window. And this specific part of the exploit will be used to exploit the out-of-bound vulnerability later. Then we have several calls, set window long, get menu bar info, and basically without too much explanation, all that call will be used to obtain an arbitrary kernel memory read and write. The kernel memory read and write will be used later to execute the code. Then we have the final part of the exploit, which is the token swapping, basically swapping the token of the current process to a system process running into the machine, and then elevate the privilege. All right, after this brief overview of the exploit, let's talk more about code graphology and what kind of information we can extract to build our hunting rule. So I discussed about some of the techniques in the previous slide, but let me explain a bit more. So in exploit development, there is some mechanism, and particularly in local privilege escalation, there is some mechanism that are very common between multiple exploits. First of all, the leaking techniques. The leaking techniques here is actually the HM validate handle call that we discussed before. And this technique is very well known in exploit development. And it is used to leak a memory kernel address for the next part of the exploit. Then we have exploit primitives. Exploit primitives are basically internal function or feature of Windows operating system that can be used to have the correct environment, to set up the correct environment to exploit the vulnerability. Another interesting artifact that could be interesting to extract and understand is the operating system fingerprinting. In most of the exploit in local privilege escalation or privilege escalation vulnerability, most of the exploit will fingerprint the operating system, whether it's a 64-bit or a 32-bit, to be sure that the exploit will be reliable and successful to be exploited into the machine. Because if you have an exploit running only for 32-bit version of Windows and you are running the program, the exploit into a 64-bit, it could lead to a blue screen of death, for example, or the exploit will simply not work. So there is, most of the time, an OS fingerprinting mechanism that will be used to discover the version of Windows. We also have the token swapping mechanism, which is pretty much the same in most of the local privilege escalation, which will be used to elevate the privilege of the current process. And also we have the strings which are simple artifacts that can be easily extracted from any piece of code. And strings can be, for example, variable name, PDB path, or any kind of unique strings available in the sample that you can reuse to build your Yara rule. So let's talk first about strings, which is the most simple artifact that we can extract from our code. So in that case, this is very interesting because we have the PDB path. So remember, this original sample have been reported to be used by Bitter APT. And in that case, we have some interesting artifacts related to the strings. For example, we have the PDB path with the path of the project where the project were compiled into the machine by the attacker. And in that case, this is very interesting because we have a strings that means KSP_EPL. So this specific string could mean Kaspersky _ local privilege escalation in reverse. It's a guess because which is also interesting, at the beginning of this exploit, there is a process fingerprinting, which is basically checking for a Kaspersky process running into the machine, which is avp.exe. avp.exe is one of the Kaspersky engine process. And this particular sample is actually checking if the avp.exe is running into the machine. It is not very clear why they perform this kind of check, but the guess will be that they try to fingerprint the machine and be sure that the machine they target were running Kaspersky engine. Another strings that we can reuse are the strings used to create our malicious window, remember, to trigger the exploit. So these kind of strings are very specific to this exploit as well, and they could be used as well to build the hunting rules. And finally, when you are talking about strings to build hunting rules, any unique strings that you can find into the binary can be relevant to build your rules. And in that case, I just extracted that one. OS operating fingerprinting. So this one is a common mechanism in exploit development, and you will see mainly if you study local privilege escalation, most of the time you will see a similar routine, a similar check. So in that case, there is two checks. The first one is checking the Windows version. Is it a 64-bit or 32-bit version? And our code is calling the ISO64 process API to check the running version into the system. And then there is a second routine used to detect the Windows build, and in that case, it's checking the sample is checking which version exactly the Windows is running to be sure that the exploit will be successful. So this is very important because this particular exploit is running only on this Windows 10 build number machine. So this is very important to do that, otherwise the exploit code is not working. And for us, for building our hunting rule, this is also very important because this is very specific to this exploit. Then we have the leaking technique. Remember, the leaking technique is to obtain a kernel memory address. In that case, the sample will call HM validate handle. This is a known trick used by most of the kernel exploit to get a kernel memory address. And in that case, HM validate handle is it's an unexported function from user32.dll. So in that case, the sample is calling the isMenu function from user32.dll, and it's calculating into the stack the address of HM validate handle. So this trick is also very important to understand and to extract for building our hunting rules, because this is the one that will be responsible to obtain the first kernel memory address into the machine. Then we also have exploit primitives that can be used to build our hunting rules. Exploit primitives are basically internal functions that can be used to get all the necessary elements into our machine to exploit the vulnerability. So the first one is client alloc win class extra byte. Remember, this one will be used to read the corrupted byte from our malicious window. Then we have the anti-user console control. This one will be used to convert the malicious window into a console window, and it will be used for the type confusion vulnerability part of this exploit. And we also have the get menu bar info, which is another primitive that will be used to exploit the out-of-bound vulnerability. And finally, we have the swapping token mechanism, which is often used in most of local privilege exploit. In that case, the sample will check the running processes into the machine and compare if each processes have the value 4, and the value 4 is meaning that it's a system privileges, a system processes. So it will, as soon as it detects a process with the value 4, it will swap the token with its own process and elevate its privileges. And then it obtains high privileges into the machine. So this part is also interesting to extract to build our hunting rules. So with all that information, what I did after several tries, I built a hunting Yara rules. So for those who are not familiar with Yara, Yara is an open source tool used to build signatures against any kind of file, whether it's a portable executable or any kind of files. And it can be used for detection, but it can also be used for hunting and discover more elements. In that case, I created this hunting rule. So this one was the latest attempt. I tried several times before, and I get a lot of false positives. So when you are building this kind of rule, you have to test it against your data set and check if there is some false positive, and then adjust your Yara rules accordingly. So in that case, we have some strings discussed before. We also have the PDB path, which is here. And we also have some opcode, which are basically some piece of code related to our exploit. So here we have the check to the Windows version. We also have some check related to the time, the build number, and finally the swapping token mechanism. And in that case, what we want, it's an executable format. And we want that the rule match for some of the strings and some of the code that we have here. So I run that specific rule, and I get that result. I discover 187 unique samples, and with all that samples, I also extracted the PDB path, and from the PDB path, I extracted the username. And I put all the username in that specific cloud word, where you can see that administrator is the most common, meaning people were trying compiling the exploit in the machine with the administrator username. Another one which is interesting to notice is ascodb. Ascodb is the name of a known GitHub repository that collect and reference local kernel privilege escalation code exploit into the repository, because the code at the time of the checking was already available, so people were trying the exploit as well. So this is interesting because we can see that this is a reliable source as well for checking the exploit. And then we also have some other username which are related to the username of the user. Which is also interesting. Remember, the original sample was the CVE 2021-1732. So most of the samples were actually this exploit. But I also discovered that our rule is matching with CVE 2022-21-882. So this is very interesting because this vulnerability is more recent, and this is also a very similar one to the one which we built the rule. So this is very interesting because with our hunting rule, we have been able to uncover a variant of this exploit. In the timeline graphic above, what I did actually, I extracted the compile timestamp of the sample and I created this timeline. And here it's interesting to notice that in March 2021, we have a peak of samples, and it corresponds to the publication of the DBAP security report. So that's very interesting because people had some interest into the exploit and started to try it. And then we also have a peak around February 2022, which corresponds to the second vulnerability that have been reported to Microsoft. With all that information, so I take a look to some of the sample, and I discovered something interesting. Actually, remember the original sample where we built the rules were related to the bitter APT. Remember, there was an interesting string into the PDB path, which is KSP_EPL, Kaspersky Local Privilege Escalation, allegedly. We have the compile timestamp on May 2020, and then this is a 64-bit version of the exploit. So when I take a look to the sample, one of them had my intention, because the PDB path have a similar naming convention, so, except in that case, it's using Sophos_EPL, potentially Sophos_local privilege escalation, and it has been compiled 2 months after the original one. And finally, this is a 32-bit version of the current exploit. And this is very interesting because this sample has not been reported until today. So it's a kind of goodies for everyone that I'm currently releasing. And basically, the first sample, the KSP_EPL, were uploaded to VirusTotal on December 2020. And the second one, Sophos_EPL, was uploaded on VirusTotal on December 2021, a year after the first sample. So unfortunately, I do not have any answer to that. Is it really related to bitter APT? Maybe. Is it something else? Maybe. Is it maybe used, is that sample have been used in the wild for different cyber campaign? I don't know. But it's still an interesting finding. All right, let's wrap up on this presentation. So here I wanted to demonstrate that code exploitation can be studied because most of the attackers that will write vulnerability or code exploitation for vulnerability will use the same mechanisms and the same techniques between multiple vulnerability and code exploitation. Here, I wanted to show that by studying the structure of the exploit and understanding how the exploit is working, we can build the relevant hunting rules to detect for more information and more sample related. And finally, we demonstrate that with simple rules, we've been able to uncover several different samples and potentially one that is related to the bitter IPT. And this is the whole concept applied to computer science for code graphology. Thank you very much for your attention. And if you have any question or any more information about these new samples, just feel free to reach out.